Hello, this is Miss Moore, and today during chemistry we're going to discuss electrons. Specifically, we're going to talk about how electrons are like particles and waves. So today's essential question, how are electrons like both particles and waves? Particles and light. So to be able to really discuss electrons, we need to have a basic understanding of both particles and waves. And this is because electrons have properties of both particles and waves. All right, let's start by talking about waves. And by the way, a wave, horrible drawing, but that's what we're talking about. Okay, so waves have three primary characteristics that you can calculate, hint, hint. So we have wavelength, frequency, and speed. So wavelength. Wavelength is the distance between two peaks or two troughs of a wave. So let me draw my beautiful wave again. And the wavelength would be, for example, from here to here. That would be the wavelength. So you can see it's like basically a cycle. So that would be distance between two peaks, or from here to here, which would be the distance between two troughs. So we're basically looking at one cycle. That would be the wavelength. And it is symbolized by this funky looking thing right here, which is a Greek lambda. And its units is in meters. Okay, so again, wavelength is the distance between two peaks or two troughs. So it's one full portion or cycle of a wave. Next we have frequency. Frequency is the number of waves from peak to peak or trough to trough per second. Okay, so let's make a little time bar here. Let's say from here to here is 1 second. So frequency, so there for this particular wave would be what? We're going from this trough to this trough, that's one cycle, to this trough. So that would be like 2 cycles per second. Wow, I really can't spell. Let's try that again. 2 cycles per second. Or we could have something like, I'll draw the next one in yellow. And going from trough to trough, we have 1 to 2 to 3 to 4 to 5 to 6. So this one is 6 cycles per second. Okay. This would be something, the yellow one is higher frequency, more cycles per second. And the white one here would be something that is a low frequency. Or less cycles per second. Okay? You will also notice that the wavelength, remember wavelength is distance between two peaks. So if you have a high frequency like the yellow one, the distance between the peaks is less, right? So high frequency equals low wavelength. And low frequency, there's a bigger distance between peak to peak. So this is going to have a higher or a larger wavelength. Frequency is symbolized by this funky looking V thing, which is the Greek letter nu. And its units is hertz, usually abbreviated as Hz. And it means cycles per second. And normally when we're doing mathematical calculations, we would use the unit 1 over S, 1 for 1 cycle per second. There's an inverse relationship between the wavelength and the frequency of a wave, which I just kind of went over with you. So inverse, remember, inverse means as one variable, in this case, let's say the wavelength increases, longer wavelength, the other variable, in this case frequency, decreases. So a longer wavelength means a smaller or slower frequency, less cycles per second. So here it is written, the longer the wavelength, the slower the frequency. So longer wavelength, slower frequency would be a wave like that. And the shorter the wavelength, peaks closer together, the higher the frequency, and that would be a wave, looks something like that. And we have this handy dandy little equation here, lambda mu equals c, and c being the speed of light. Both the equation and the quantity for c is on your reference tables. But what we can do with this equation is we can actually figure out the speed a wave is moving. We can figure out the wavelength. We can figure out the frequency if we know some of that. Okay, so it's a handy dandy equation that you should be able to use. Pretty straightforward conversion sort of thing. All right, on to electromagnetic radiation. So light is a type of electromagnetic radiation. So what in the world is electromagnetic radiation? Well, it's a wave. It's a wave made specifically of electric and magnetic fields, but it's a wave. For us, it's a wave. That's good enough. The electromagnetic spectrum is all wavelengths of electromagnetic radiation. And visible light, only that's the stuff we can see, only makes up a small portion in the middle of the electromagnetic spectrum. And then frequencies of light that are low, ones that have long wavelengths, so lower frequency, longer wavelength than visible light, include radio waves, microwaves, and infrared radiation. Whereas high frequency waves, shorter wavelengths, higher frequency than visible light, include ultraviolet, X-ray, and gamma rays. All right, visible light. The visible light portion of the electromagnetic spectrum. There are different colors of visible light, which you obviously, hopefully already know. And the colors of light are due to the frequency of the electromagnetic wave. Remember again, frequency, low frequency, high frequency. So the different colors, so this, if we had a wave of light like this, we would see that as a different color than a electromagnetic wave with that sort of frequency. So for the visible light spectrum, red has the longest wave. So a red wave, slowest frequency, we would see something like that. And violet has the highest frequency. So something like that. So the actual order of visible light from shortest wavelengths to longest, and that is written exactly backwards. Please don't write that yet. So from longest to, let's change that to shortest. Sorry about that. Is red, orange, yellow, green, blue, indigo, and violet. You should kind of know that range. And it's actually the same, if you look at that same order as a rainbow. Okay, so where red has the longest wavelength, lowest frequency, and violet has the shortest wavelength, highest frequency. Planck's quantum theory and visible light. So, turns out that when you heat solids, they emit electromagnetic radiation over a wide range of wavelengths. And some of these wavelengths we can actually see, right, if they're in the right range. And Planck found that the amount of energy a solid object can absorb or emit depends on the wavelength of the energy. Okay, so it can emit more or less depending on the actual wavelength. So he titled a quantum, or he defined a quantum as the smallest quantity of energy that can be emitted or absorbed by a solid. And he came up with this equation here, E for energy equals h nu. This also is in your reference table. So E is energy. H is Planck's constant, which is 6.63 times 10 to the negative 34 joules, also on your reference table. And nu is frequency. Okay, so what Planck again found out is that energy is related, the amount of energy that can be released or absorbed is directly related to the frequency by a factor of his constant. Okay, let's try a few calculations. So our practice will be, what is the energy of a single UV or ultraviolet photon having a wavelength of 11.3 nanometers? And then what is the energy of a mole of UV photons having a wavelength of 11.3 nanometers? All right, let's start with the first one. Let's list what we know. We know its wavelength is 11.3 nanometers. So wavelength equals 11.3 nanometers. And we're trying to find the energy. Energy equals, I don't know. All right. Let's think about what equations we know. An equation that has wavelength in it is c, or speed of light, equals wavelength times frequency. I also know an equation that has E, or energy, in it, which is energy equals Planck's constant times frequency. All right, because we know wavelength, but want to get to energy, we're going to end up having to use both of these equations to solve, starting out solving for frequency. So let's start with using this equation. So the speed of light, c, is 2.998 times 10 to the 8th meters per second equals, so now we're going to plug in our wavelength. However, before we do that, you should note that unit is nanometers, but in the speed of light it is meters. So we're going to need to change this to meters. So 11.3 nanometers. To get to meters, we need to move the decimal to the left 9 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll end up with 7 zeros. And now we're in meters. That doesn't say meters. There you go, meters. I don't particularly like all of those zeros, so I will change that to 1.13 times 10 to the negative 8 meters. And that's what we're going to plug in for lambda, so we can cross out our units. So 1.13 times 10 to the negative 8th meters times the frequency. All right, let me get rid of a little bit of writing here. So to get the frequency by itself, we need to divide both sides by 1.13 times 10 to the negative 8th meters. Allowing our meters to cross out, we're left with seconds. And when we do the math, I came up with the right number of sig figs, which would be 3, came up with 2.65 times 10 to the 16th over second. All right, let's make some room for ourselves. I'll put our answer in our known list. So now we know our frequency equals 2.65 times 10 to the 16th hertz or per second. And now we can calculate energy. So we can use energy equals Planck's constant, which is 6.63 times 10 to the negative 34th joules seconds equals, oops, wait, not equals, take that back, times the frequency, which is 2.65 times 10 to the 16th per second. We can cross out our seconds, and when we do the mathematical calculations, I came up with 1.76 times 10 to the 17th, that doesn't say 17th, 17th joules. Okay. So that is the amount of energy that one UV photon can have. All right, let's move on to the second part of the question, which is, what is the energy of a mole of UV photons? So before we go to that, let's talk about this energy, the answer we just got. Here, we're talking about the energy per photon. Okay, so this is we're talking about the energy in one photon. So the actual answer, if I erase this real quick, at least a little bit of it, is actually joules per photon. Okay, and so when we're doing the calculations, normally it's for an individual photon. But now we need to figure out the energy in a mole of photons. So how do we go about doing that? All right, let me erase some stuff and give us a little bit more room. All right, so I have a little bit more room to work now. So what we need to do now is go from joules per photon to moles per photon. Okay, it's just a basic mole conversion. And inequality you already know, I hope, is, remember, 1 mole equals 6.022 times 10 to the 23rd. And so far we've used that with atoms or molecules. But the truth is, it's a counting unit, right? And so it could be 6.022 times 10 to the 23rd of anything, okay? We could have 1 mole of donuts, which means we have 6.022 times 10 to the 23rd donuts. But we don't really care about donuts right now, except for I'm a little bit hungry. What we care about is photons. So 1 mole of photons is 6.022 times 10 to the 23rd. Right? So now we can actually do a basic mole conversion. We know we have 1.76 times 10 to the negative 17 joules per photon. Right? So now we need to convert that to joules per mole. We can use this equality, 1 mole equals 6.022 times 10 to the 23rd photons, setting it up so our units cross out. So we want to get rid of photon, right? So photon is going to go on the top. 6.022 times 10 to the 23rd photons. And on the bottom is going to go 1 mole. Photon, photon. So when we do the calculations, we're going to end up with joules per mole, which is what we were looking for. So let's plug and chug and see what happens. And I got let's see, I got 1.0 with the right number of sig fig 6 times 10 to the 4th joules per mole. Okay, so there you go. All right, on to the photoelectric effect. Like I just talked about, metals emit electrons. Well, I didn't talk about this. I actually talked about Planck's constant, where we find out that when solids are heated, which means adding energy, they emit radiation, electromagnetic radiation. It turns out that actually these same solids, metals, emit electrons. Radiation, which is a wave, right? These electromagnetic radiation is a wave, but metals also emit electrons when light of sufficient frequency shine on them. Interesting. This suggests that light is actually a stream of particles. Because these particles can actually knock off electrons, right? A wave can't knock something off. Wave is energy. But a particle could, if it's hitting with enough frequency, could actually knock an electron off a metal. So that, for now, that's it for photoelectric effect. We're going to now take the photoelectric effect, Planck's idea, merge it into a theory of the model of the atom, and we'll be hitting back on photoelectric effect a little bit later. Okay, Bohr's theory of the atom. Bohr noticed that when an atom absorbs energy, it re-emits that energy as light, and that each type of element has a characteristic color of light. Furthermore, this light can be split into the wavelengths making up the light by passing it through a prism, which results in a line emission spectrum. So, for example, if I excited some, I'm not really sure what, hydrogen. Okay, so add some energy. It glows, in this case, blue, where it's actually more of a purple color, but whatever. If we pass that through a prism, it will split that blue light into distinct colors of light. And that thing is called a line emission spectrum. What's really cool is that white light has a continuous line emission spectrum, meaning that the lines, I don't have enough colors of pens, but that you're going to see every shade, every color of the rainbow in just a continuous shade with no separation. So something like, I guess, let me try to do this. So we might start with like red, lighter, and then we go on to yellow and orange and so forth. I'm not going to draw every color, but just all the way across, all the way until we get to violet. Okay, so that's what it would look like if you split up white light with all this stuff in the middle filled up. Okay, but with these line emission spectrum of light coming from elements, it's not continuous. It's only containing very specific and discrete wavelengths. So you would see something like, maybe you'd see some purple and some yellow and then maybe some red, but not all the stuff in between. Okay, so that must suggest, well, let's see what it should suggest. So it suggests that that the electrons are in certain fixed distances from the nucleus, and that these distances represent a certain amount of energy. The reason it suggests that is if there weren't certain exact amounts of energy related to certain exact amount of distances, we wouldn't end up with these nice discrete lines that we see when we split the light coming from elements. We would get that continuous spectrum. Let's see, where is it? There you go. If they weren't discrete certain amount distances with discrete certain amounts of energy, they should always look like this, where the energy could come from anywhere, any amount. But instead, it looks more like this, suggesting that there's no possibility of any amount of energy or wavelengths, frequency from that region, or for that matter, this region or this region. That the energy is only here, here, and here. And what Bohr suggested is that each of those discrete portions of energy, again, let's go back to the relationship. Why am I saying energy? Because energy is directly related to wavelength with Planck's constant. And remember, these different colors come from the wavelength. So again, Bohr is saying that, hey, there has to be discrete amounts of energy, and I think this has to do with distance from the nucleus, because it's going to take more or less energy to move farther and farther from the nucleus. So what Bohr is thinking is going on is that when you throw electric current or something through a sample of an element, the energy is absorbed by the atom, causing the electron to move from, so if this is a nucleus, causing the electron to move from one discrete level, distance from the nucleus, directly to a second. So it just directly goes from here to here. It can't go into any of the areas in between. Okay? So it's a fixed distance from the nucleus. And then light is released, and the resulting line emission spectra is the result of the original electron returning to the original distance from the nucleus. So Bohr went on to explain the theory of the atom. And what he came up with is that it's an orbit molecule with particle-like electrons orbiting the nucleus at fixed distance. You've all seen this kind of thing. So we've got the nucleus, and then around the nucleus are electrons. And there's another energy level with more electrons. If you add some sort of energy, say example electrical current, this electron could jump up to that energy level. This electron could jump up to the next energy level, but it couldn't hang out anywhere in between. And then the electron would then fall back to a lower energy level, releasing light. Let's take this just a little step further. Let me get a couple energy levels. So let's say we added some energy, and we're talking here, let's say a helium atom or lithium atom. We've got 3 electrons there. We add some energy, and this electron jumps from energy level 1. So this is energy level 1, 2, 3. So this electron jumps from energy level 1 to energy level 2. And this electron jumps from energy level 1 to energy level 3. When they fall back down to the original position, so when this one goes back to energy level 1, that's more energy, right? You're going from energy level 3 back down to 1. That's more energy. And remember, energy is directly proportional to the frequency times Planck's constant. So that should mean higher frequency light versus this one when it drops back, less energy, lower frequency light. Not very good drawing. Let's try that again. Lower frequency light. Okay, last topic in this very jumbled lecture here, quantum mechanical model. What you need to know about this is it turns out that Bohr wasn't quite correct. Electrons do not exactly act like particles in discrete locations. Okay, so they're not exactly here and they, fall down or up. Okay, they're not exactly like particles, but somewhat. Electrons act somewhat like particles, but also somewhat like waves, with each electron in a likely region within a wave function. So let me explain that. If you think about a wave, don't think about light right now. Think about a wave on the ocean, right? So it's going like that. There's a one particle right here. And as the wave goes past, it's going to be up here at the peak, and then as the wave moves on, the particle doesn't slide down. The particle is now in this position, this position, this position. So the particle moves up and down, okay, as the wave is going by. So electrons act sort of like that. Unlike it being in an exact location, this dot, at any one time, an electron would be somewhere along that wave function, at the peak, at the trough, or somewhere in between, okay? So we've got the Heisenberg uncertainty principle, which says that there's a fundamental limitation to just how precisely we can know both the position and the movement of a particle at any one time. Okay, so Bohr sort of had the right idea. There are these discrete locations, but it's not an exact location, okay? It's sort of in a region, and we'll go a little bit more into that next time. Okay, so believe it or not, we finished this very jumbly lecture with a lot of terms and stuff. So that's it for today. Have a good one.